Hi everyone, we're the Cloud Dataverse team and our product is called CloudCompute. So let's start with what CloudCompute is. CloudCompute is a web application that links your data repository to your compute infrastructure through a seamless experience. So let's start by looking at a use case, which is Facebook Messenger. Imagine that there's a team at Facebook collecting metadata on Facebook Messenger, and this team would prefer to have a cloud data repository to store their data collected by their analytics program for scalability and availability. At the same time, another team within Facebook wants to run MapReduce jobs on this data. Then they can use our CloudCompute UI to do so. Also, another use case would be if there's a data scientist at Berkeley who's interested in using the same data for their data science class, they can use this data with our UI without any complex cluster setup. For our generalized solution, we're assuming that the user has a cloud-based data repository for sharing their published data with user group-based access control, and also a compute and data processing infrastructure. So our job is to create a middle layer to couple these two together. With our UI, the user can have a seamless user experience, simple cluster and job creation, and also experienced users can also have advanced options. For our particular solution, we use Dataverse as our cloud-based data repository. Dataverse is an open source web application that promotes the sharing, exploration, and analysis of research data. Dataverse also has a cloud component to it. The Cloud Dataverse team have been working on shifting the current Dataverse to the cloud. So the Dataverse includes data sets and data repositories, and the goal of the Cloud Dataverse team is to transfer these files so that they can be stored on the cloud in OpenStack Swift. Our compute infrastructure was OpenStack that's run on MGHPCC or MOC, Massachusetts Open Cloud. And our goal for this project was to create this coupling web application called CloudCompute, which is our middle layer solution that was described in the earlier slide. So now let's look at the architecture of CloudCompute UI and how it interacts with the Dataverse UI. So the Dataverse UI is something that's created by Harvard, and that's where the data sets are stored. And the data sets are stored in Swift, so they have container names, and we get these container names via a HTTP post request. So when we hit compute on the Dataverse UI, it takes the user to our CloudCompute UI. And the first step the user has to go through is the login. And for login, we used the Keystone API of OpenStack. After logging in, the user can see the data sets in the container, and they can choose the data sets that they want to compute over. These data sets are stored in the container, so this is where the HTTP post request comes in, and this is where Swift comes in as well. So the cluster creation is done in the data processing API of OpenStack, and we also use Sahara for this. The user can create clusters in 3 different ways, from existing clusters or from existing templates or entirely from scratch. The Neutron API is used to get the networks, and Nova is used to get the user's SSH keys. So this was a simple architecture of CloudCompute UI. Next up, Ben is going to go into more details regarding our implementation of the web application.
So now we'll move into the particular implementations of the various aspects of our web application. The first being the ability to select datasets from Dataverse. We decided to go with a shopping cart style implementation such that the user could select multiple datasets from the Dataverse user interface and then work with those within the CloudCompute UI. Modifications were made to the Dataverse backend, which is built on Java EE, and a modification to the session bean was made to implement this shopping cart. When a user clicks on the compute button in this image in the bottom right, which you'll see a demo of later, an HTTP post is made, to the CloudCompute UI, sending a stringified version of the container names to the CloudCompute UI, and then the user is authenticated with OpenStack, and those container names are created in a session cookie on the CloudCompute UI. This demo shows the Dataverse side being able to select a dataset, adding it to a compute batch, and then viewing the datasets that we currently have in our quote shopping cart. We'll go back and select another dataset, adding that to the compute batch, and then clicking on the compute batch shows you the datasets that you have in your shopping cart. Once a user has clicked on the compute button in the prior screen, they are sent to the CloudCompute UI, where they then must be authenticated with Keystone. Keystone is the authentication API provided by OpenStack. We send the username and the password to the Keystone API to authenticate the user, and what we get back is a token that's set in a cookie that allows a user to continue using any of the OpenStack APIs as long as they're authenticated and their cookie is still present. After 1 hour, the cookie expires and the user must re-authenticate themselves with our user interface. The diagram in the bottom right shows the progression of events that a user must go through to log into our user interface. They go from the Dataverse UI, they select container names, those are sent to the CloudCompute UI, the login screen is presented, the user is authenticated, and then they can begin processing their data. In this demonstration, we'll show going from the Dataverse website to the CloudCompute website and authenticating using our OpenStack credentials. The user puts in their username and password, logs in. Once authenticated, the container names are pulled down and the files are displayed. You'll see a later demo of that in the next few slides. To be able to pull these files that are present in the containers that we've retrieved from Dataverse, we use the Swift API provided by OpenStack. The container names are stored in a cookie, in particular a session cookie. The Swift API collects those container names, makes a request to the Swift API, pulling all of the objects available in those containers. Once those objects are retrieved, they're displayed to the user, and the user can then select any of those files to process data over. The actual data processing is handled by the Data Processing API, also known as Sahara. We use the Data Processing API to handle cluster creation, job creation, and monitoring for clusters and jobs. Cluster creation involves creating templates. It involves using those templates to create clusters and then launch those clusters. Job creation involves creating input and output sources, which you'll see after this demo. The user selects files to compute over, and then they have 3 options. Select an existing cluster in the project, create a new one from a template, or create one from scratch. Once a cluster is selected, the next step is to actually run compute jobs. To do this, the user inputs their username and password. These authentication details are used to set up the input-output data sources for jobs to be run on. A job binary is selected, in this case, a MapReduce jar file, and the jobs are submitted. This takes you to the job monitoring page, where you can track the progress, or go directly to OpenStack. So what is unique about our user experience? We've simplified the big data process. We've drawn many of our user experience design elements from the Amazon Elastic MapReduce platform to create a simple user experience in just 3 steps. The CloudCompute UI simplifies many of our data processing operations, eliminating the need for prior experience in cluster creation or command line interfaces. We built our user experience, our user interface, I should say, with a simplistic and responsive design choice through Bootstrap 4 and AngularJS. Our web application is run on Node.js, which will be spoken about later. In this demonstration, on the left side, you'll see a user creating a cluster and running a job in the CloudCompute UI. If you pay attention closely enough on the right side, what you'll see is the same exact operation being done in the OpenStack user interface. You'll see many clicks, lots of work, all to accomplish the same thing in more amount of time. So on the left side in the CloudCompute UI, everything's completed in 6 minutes and 38 seconds with one click. The same exact process in the OpenStack UI takes over 10.5 minutes. It's pretty amazing.
I'd like to introduce about our learning outcomes. First of all, in this project, we are fully engaged in the agile development. We learn to continuously plan the project in sprints every 2 weeks. And we learn to use the agile tools, including Trello and the burn charts to track the sprints. For each sprint, we define the possible use cases and made a plan for the tasks we are going to do, while effectively estimating the time required for each task. After finishing each sprint, we reevaluate what we have done and make a plan for the next sprint. Using the project is based on OpenStack platform, so we did our investigation in OpenStack Keystone, Swift, Nova, Neutron, and Sahara. Knowing how this OpenStack project and API work, we made our plan of making the integration of these OpenStack functionalities into our project, using the APIs such as Keystone or Data Processing API. We also gained the experience of full-stack development on MinStack and Java EE. We developed the CloudCompute UI using MinStack with Express for routing, Node.js in the backend, and AngularJS for designing a dynamic frontend. We modified the open-source Dataverse code in Java EE, for which we learned the Java EE architecture such as EJB and JSF technology, and then learned to deploy it on the Glassfish server. There are several challenges during our project. First is installation of the Dataverse, since it is a huge and complex system. So we worked with Dataverse and Cloud Dataverse team to install the fully functional Dataverse web application on our instance, as well as the local machines. Another challenge is to effectively understand the use of OpenStack APIs in order to integrate the OpenStack with our project. And so we took much effort scrutinizing the documents and made the feasible plans of the OpenStack integration. Also, for this project, we were facing with new and unfamiliar platforms such as Node.js, for which we learned the effective developing and debugging techniques on those platforms such as Node.js and Java EE. In order to design a seamless user experience, it is also a challenge to define the minimal user requirements in order to provide an application with simplicity. So we did some case study for the real cases using Hadoop and Spark on other platforms, and finally we have our design of the CloudCompute UI. Next, Will is here to go into the project limitations and the future of the CloudCompute.
Our project does have some limitations. The first is that we assume Dataverse handles granting file access permissions. What this means is that instead of handling permissions in our application, we actually rely on Dataverse to handle user group permissions. Now this is problematic because it greatly decreases the control that a publisher has over file control access. The preferred implementation would be being able to grant pre-signed URLs to the Swift objects or the datasets stored in Swift if a user group requirement is met. This would allow a user to get a URL to a Swift object for some predetermined amount of time use it to compute, process data, and then they would lose access to that URL after the expiration. Additionally, our user interface and user experience does not support advanced or power users. Our UI was taken from Amazon's Elastic MapReduce setup page. However, Amazon implements an advanced settings page, allowing the user to go and access all of the settings available when launching a cluster and for the setup of jobs. Our user interface should provide advanced users with some method of being able to go from Dataverse to our application, collect the pre-signed URLs of the files that they would like to compute over, and then from there be able to set up all of their clusters and their jobs on their own within their OpenStack dashboard. So what does the future look like for cloud compute? We're happy to say that our user interface design will likely influence future and current development at the Massachusetts Open Cloud project called GIGI. GIGI is a simple, intuitive GUI project to provide users who do not have extensive experience with the OpenStack platform to easily spin up clusters and manage other services provided by OpenStack. And this simple, intuitive GUI also extends to the OpenShift platform. And secondly, we had hoped that we can showcase the CloudCompute UI to OpenStack such that they could perhaps implement the simple UI approach in their own platform so that users who are not experienced with OpenStack, data processing, cluster management, or object management could use an interface similar to CloudCompute to quickly and efficiently set up the things that they need without prior experience. So that is all. We hope that you enjoyed this presentation. If you have any questions, please feel free to contact us either on YouTube or by emailing us directly in the emails in the description.